All right, so in the last lecture, we talked about the difference between distance and displacement. So let me just quickly review that. Displacement is the vector that starts, suppose an object starts at point A and goes to point B. Displacement is the vector that starts at the starting point and ends at the ending point. So it's a vector. It has a definite magnitude and a direction. The distance traveled represents the actual path that the object took. So it might not have followed this particular path. It might have followed any other path and gotten over here from A to B. Distance traveled is the actual path that the object took. Right? Okay. Um, so you can see that the displacement, the magnitude of the displacement is the length of the straight line path between the 2 points, and the distance traveled is the length of this curved path that the length of the actual path taken by the object in getting from A to B. So it's very important to be clear about the difference between distance and displacement. Distance is a scalar. As you can see, there is no particular direction associated with this path that I drew, whereas displacement is a vector. It has a direction, which is the direction from the starting point to the ending point. Okay, now we also talked about position time plots, where you plot the distance traveled. You plot on the x-axis, on the vertical axis you plot x, and on the which is position, and on the horizontal axis you plot time. And so this is a position time plot, and we saw that from a position time plot it's possible to get an idea of how fast an object is moving. And I think I went through this example where an object starts from over here and goes over here. So is this object moving faster? Or suppose another object starts from the origin and goes over here. Which of these is moving faster? I think we did an example like this in the last lecture. Clearly, the object that follows path A is moving faster because it's covering a larger distance. Uh, it's covering the same distance. The distance is the same for both of them. It's the amount of displacement in the horizontal, along the vertical axis. If you follow path A, then you're covering that same distance in a shorter period of time versus for path B, you're following it in a longer period of time. So anyway, we talked about these in the last lecture. Okay, so the next thing that we are going to talk about um, is average speed. So this is on slide 8. So we're going to talk about average speed. Average speed is simply total distance divided by total time. So it's something that you're very, very familiar with. So for example, suppose you start driving and from home, and you get to Chattanooga in 3 hours. The distance from Nashville to Chattanooga, I think, is 150 miles. So if you get there in 3 hours, that would mean that your average speed was 50 miles per hour. 150 miles divided by 3 hours. So average speed is simply the speed that you'd have to need to maintain uniformly to cover a given distance in a given time, right? And so if you drove non-stop for 50 miles per hour, then you would cover a distance of 150 miles in 3 hours. Okay, so that's something that you're all very familiar with. The next thing that we're going to talk about is average velocity. So average velocity is the total displacement divided by the total time. Is the change in displacement divided by the change in time. That's the definition of average velocity. So in one dimension, we've seen that delta r is just I hat delta x. So this is something we discussed in the last class as well. We saw that delta r in general is I hat delta x plus j hat delta y plus k hat delta z. So delta r is simply, and in one dimension, you don't have these delta y's and delta z's. And so delta r is just I hat delta x divided by delta t. Okay, so that is your average velocity. And in one dimension, it's not super essential to keep these I hats and j hats, just because it's very easy to keep track of direction. You know that a positive quantity will indicate the positive x direction, a negative quantity would be along the negative x direction. And so it's fine to just work with the magnitudes in one dimension. In 2 or 3 dimensions, of course, you want to keep the vectors. So V average, we can write without the vectors, we can write V average as delta x divided by delta t. So the change in position divided by the change in time. That's the definition of average velocity. This has a geometrical interpretation on the position time graph. So suppose you have an object that moves from here uh, and ends up over here, then this was the initial, so you can see what the initial x is, it's right here, and the final x is over here. And the initial t is over here and the final t is over here, right? So what does delta x divided by delta t represent? You can clearly see that it represents the slope of the line segment joining the initial point and the final point of the object on the position time plot. So delta x is, this should be over here. So this is delta x and this is delta t. So the average velocity is simply the slope of the straight line joining the object's initial position on the position time plot and final position on the position time plot. All right. Okay. Now let's look at a top hat example. See if you can figure this problem out. So a particle moves along the x-axis from x equals -5 to +5 in 2 seconds, and immediately turns around and returns to x equals -5 in another 3 seconds. What are its average speed and average velocity? So average speed is simply the total distance divided by the total time, right? So what is the total distance? The total distance is, it's going from -5 to +5, and then it's coming back. So 20 units, 20 meters, divided by a total time is 2 seconds plus 3 seconds, which is 5 seconds. So that's going to be 4 meters per second. That's going to be the average speed, total distance divided by total time. What about the average velocity? The average velocity is the change in position, x, divided by the time it took to change that position. So that's going to be 20 meters. Let's think about the change in position. So it's starting from -5 and going up all the way up to +5, and then it's coming back, right? So what is the delta x? Delta x is the final x minus the initial x. Here the final and the initial x are the same because the object is just coming back to where it started from. So delta x is 0 divided by delta t. So the answer is 0. So this is the correct answer. All right. So from this, you can see that the average velocity is not that useful of a quantity because it does not really, it gives you an average, like in this case, the average velocity being 0 might make you think that the object didn't move at all, but that's not the case at all. The object did move 20 meters total, but it's not reflected in the average velocity. Yeah. Okay, what is a far more important and useful quantity than the average velocity is the instantaneous velocity. What is instantaneous velocity? Now all of you have a intuitive understanding of what instantaneous velocity is. It's simply the velocity of of a moving object at one instant in time, right? So, for example, you can think of those radar, not those. You can think of those traffic lights which measure your speed as you're going through an intersection. So those are devices which measure your speed at one instant in time, right? Similarly, the police radar, which measures your speed, um, it measures the speed at one instant in time when the radar, the radio waves bounce off of your car. So instantaneous velocity is something that's intuitively easy for us to understand. It's the velocity at one instant in time, but being able to define it mathematically took almost 300 years. And for a long time, for many, many years, people struggled with this concept of trying to mathematically understand instantaneous velocity. But it was only after the invention of calculus that the mathematical representation of this became clear. All right, so let's try to understand instantaneous velocity. Let's consider this position time plot. So let this be 5 seconds. This is time. Let this be 5 seconds. And let's say this is 10 meters. And let's say an object starts out at the origin. I'll just make some markings here. Okay. Suppose an object starts out at the origin and then proceeds to, okay, then goes 1 meter and then does this. And eventually reaches the 10-meter point, right? So it started out really slow. I mean, it started out relatively slow. It only covered 2 meters in 2 seconds, but then it covered almost the entire distance between 2 and 3 seconds, and then it was practically at rest for the next 2 more seconds. Yeah, and so that is the position time plot for this object. Okay. Suppose you are interested in finding the instantaneous velocity of the object somewhere over here, or maybe at somewhere over here at 3 seconds. All right. So the object is moving pretty fast over there because it's covering a really large distance in a very short period of time. And you want to know what is its speed exactly at 3 seconds, right? One approach could be you could find the average velocity, delta x divided by delta t, um, over the entire time interval. So you could do delta x divided by delta t, and for delta t, take the entire time interval of 5 seconds. And that gives us, so how much distance is covered in 5 seconds? The whole 10 meters divided by 5 seconds. And so that comes to something like 2 meters per second, which is not at all a good representation of the object's speed at 3 seconds when t was equal to 3, because it t equals 3, it was moving much faster than 2 meters per second, right? So it was not a good idea to take such a wide interval of 5 seconds for delta t. Something that would be somewhat better is if we took a shorter interval. So maybe we could just take the interval from 2.5 seconds to 3.5 seconds. So in that case, we would get, let's see what we get. So the delta t is 1, and the delta x is, it's going from approximately 246. It's going from approximately 2 meters to 6 meters. So 4 meters in 1 second. So that gives you a higher speed of 4 meters per second, but it's not quite the speed that the velocity that it had at 3 seconds. It's an average velocity over the interval 2.5 to 3.5 seconds, right? So how could we do better? We could shrink this interval even further and consider a much smaller interval from maybe 2.9 seconds to 3.1 seconds. In that case, we would get this slope, which is a much better approximation, right? So to get closer and closer to the actual instantaneous velocity, we need to shrink delta t, um, the interval delta t, as much as possible. We want to make it smaller and smaller and smaller. And the smaller we make this interval, the more accurate our estimate of instantaneous velocity becomes. So essentially, to get the exact value of the instantaneous velocity at t, what we need to do is delta x divided by delta t, where we take the limit delta t tending to 0. This will give us the exact instantaneous velocity at t equals 3 seconds. So we considered 2.9 to 3.1. We considered delta t of 2.9 to 3.1. How about 2.999 to 3.001? Or we could do even better than that. How about 2.99999 and 3.0001? So just make this interval as small as you possibly can, and just make it infinitesimally small. And if you, in the limit that delta t goes to 0, you will get the instantaneous velocity. So that is the definition of instantaneous velocity. Now, this quantity might ring a bell from elementary calculus. This quantity is just the definition of a derivative. So, in other words, the instantaneous velocity is simply the derivative of the position function dx dt. Now, just an aside here, in your calculus, high school calculus classes, the definition of the derivative of the function x of t, you might have seen it like this: limit h tends to 0, x of t plus h minus x of t divided by h. So this might have been the way you've seen the definition of a derivative in your calculus books. But if you think a little carefully, you'll see that this is exactly the same as what we have. So x of t is our function. When you change t by a small amount, then and subtract off the original t, then I mean you've incremented t by a small amount and then subtract off the original value of the function, then this is nothing but delta x, the change in x when you change t. And what is this h? H is the amount that you've changed t by, right? So h is nothing but delta t. So what we have here is simply the definition of the derivative that you've seen in calculus classes. All right. So our conclusion from here is that the instantaneous velocity at any given point is simply the derivative of the position function at that particular point. And geometrically, what does this mean? You might remember from calculus that the geometrical interpretation of the derivative is that it is the slope of the function, it is the slope of the tangent to that function. So essentially, if you, going back to our position time plot, we had something like this. I'm just drawing it again because the original diagram is a bit cluttered now. We had something like this, and we were interested in finding the um, uh, instantaneous velocity somewhere over here at t equals 3. So if we calculate the derivative of the function at that point, what we are doing is we are calculating the slope of the tangent to the function at that point. So if we draw a tangent to the tangent line like this, we are calculating the slope of the tangent at that particular point, right? And so you can see that that is a really good way of getting the instantaneous velocity. It makes perfect sense. It's the slope of the tangent to that to the curve position time plot at that point. All right. So our key takeaway is that velocity is given by dx dt. Instantaneous velocity is given by dx dt. And by the way, instantaneous velocity is what we always mean when we use the word velocity. So when we say velocity, we usually mean instantaneous velocity. All right. So we can do the same thing that we did with position and measure its rate of change. We can do the same thing with velocity. Now, there is no reason for velocity to be always constant. An object can have its velocity change. That happens all the time. So the quantity that measures the change of velocity, the rate of change of velocity, is called acceleration. Acceleration, it measures the rate of change of velocity. Okay. So you can have an average acceleration, A average. Oops. Let me just rewrite this. A average, which is the change in velocity divided by the time it took for that velocity to change, which you can write like this. You can write the delta V as I hat. Now, everything is along the x-axis if you have one-dimensional motion. So I hat times the magnitude of delta V divided by delta t. So that would be your average acceleration, right? Let's look at an example of this. So suppose you have an object that's moving at 3 meters per second, and then it speeds up, and over here it's moving at maybe 5 meters per second. And this change happened over a time interval of 10 seconds. So what is the average acceleration? So the average acceleration, and I'm writing this without the vector notation here because I know everything. We know that everything is along the x-axis. So A, I can just write an equation with the magnitudes. A is equal to delta V divided by delta t. Delta V is the final velocity minus the initial velocity. So that's 5 meters per second minus 3 meters per second divided by 10 seconds. So that comes to 1/5 meters per second divided by seconds. So meters per second divided by seconds is often written as meters per second square. And that is the unit of acceleration, right? So here is an example of average acceleration. The average acceleration over these 10 seconds, over this 10-second interval, was 1/5 meters per second square. Okay. All right. So acceleration has units of meters per second square, as I just said, and this simply means meters per second over seconds. So suppose an object, let's look at an example. Suppose an object starts at t equals 0 with a speed of 5 meters per second, and it's speeding up with a constant acceleration of 2 meters per second square. What does that mean? It means that the change in the object's acceleration every second is by the amount 2 meters per second, right? So every second, 2 meters per second is being tacked on to the speed of the object or the velocity of the object. So yeah, so it speeds up by 2 meters per second every second. So what will its speed be after 1 second? The answer is It was originally at 5, and then 1 second later it will have picked up another 2, so it would be 7 meters per second. And what will its speed be after 2 seconds? Well, it would have picked up another 2 in one more second, so it would be 9 meters per second. So hopefully the meaning of the unit meters per second square is clear to all of you. Note that velocity and acceleration are very different things. A common mistake that I find students making is that they think of the velocity and the acceleration as the same thing and often use them synonymously. But velocity and acceleration are completely different things. Velocity measures how fast the position of an object is changing. Acceleration measures how fast the velocity of an object is changing. All right. Now, what we just calculated was the average acceleration. So the average acceleration over a certain interval of time. But what we are often much more interested in finding is the instantaneous acceleration. Like, what is the acceleration at one particular instant of time? Okay, so the instantaneous acceleration is calculated in exactly the same way as we found the instantaneous velocity. So so we know that the average acceleration is delta v divided by delta t, right? The instantaneous acceleration would be the acceleration would be delta v divided by delta t, but with delta t made very, very, very tiny. The interval delta t is a very small interval around the point of time where you want to find the acceleration. So if you want to know the instantaneous acceleration at t equals 2 seconds, then delta t is a very, very, very tiny interval around the 2 seconds. So it might be something like 1.999999 to 2.0000001 or something like that. So in other words, the instantaneous acceleration is the limit delta t tending to 0 of delta v divided by delta t, and this is nothing but dv dt, the derivative of the velocity function. And you know that v itself is the derivative of the position function, so you can write this as d dt of dx dt, and this thing, as you know, is just d2x dt square, the second derivative of the position function. All right. Okay, so similar to the uh, instantaneous velocity, the acceleration is the slope of the tangent of the velocity time plot. So if you make a velocity time plot, acceleration would simply be the slope of the tangent of the velocity time plot at a given time. And acceleration is also a vector quantity, and it points in the direction in which the velocity is increasing. Okay. All right, so let's try this question. An object's acceleration is minus 3 meters per second square. Which of the following is true regarding its motion? I would recommend pausing the video at this point and seeing if you can figure this out on your own. Okay, the correct answer is C. It could be either be speeding up or slowing down. Now, a lot of students get this question wrong because you might intuitively think of a negative acceleration as a deceleration, but that is not quite the case. So let's look at some examples, numerical examples, to make this clear. Suppose you have an object that's moving at 5 meters per second, and it has a constant acceleration. So its instantaneous velocity is 5 meters per second, and let's say its acceleration is minus 3 meters per second square, right? The velocity being plus 5 meters per second means that it's moving along the positive x-axis. All right. The acceleration is pointed along the negative x-axis, right? What is the velocity going to be after 1 second? So as we saw in a previous slide, acceleration of a constant acceleration of minus 3 meters per second square means that every second the change in the velocity is minus 3 meters per second, right? So after 1 second, the velocity of the particle would simply be 5 minus 3 or 2 meters per second. So it will have slowed down after 1 second, right? Okay, so this seems to indicate that an acceleration of minus 3 meters per second square would make the object slow down. All right, what about if the object was moving to the left 5 meters per second, same instantaneous velocity? Uh, I mean, same speed, but pointed in the opposite direction. So the velocity is minus 5 meters per second. What would its velocity be 1 second later? So the change is minus 3. So 1 second later, it would actually be moving at a much faster speed of minus 8 meters per second. So if the object were moving along the negative x-axis, then an acceleration of minus 3 meters per second square would actually make it speed up. Whereas if it were moving in the positive x-axis, then an acceleration of minus 3 meters per second square would make it slow down. And so the correct answer is C. It could either be speeding up or slowing down. So you can see now that the acceleration will cause an object to speed up if it's pointed in the same direction as the velocity. Whereas if the acceleration is pointed in the opposite direction as the velocity, then the object will slow down. That's what I explained in this slide. This slide is pretty important because we will be looking at this, we will be revisiting this in the next chapter when you have 2 or 3 dimensional motion. So if an object's velocity and acceleration point in the same direction, then that object will speed up. And if the velocity and the acceleration point in opposite directions, then the object will slow down. All right, so please pause the video if necessary and make sure that this point is absolutely clear. Okay, think about this question. If an object is accelerating towards a point, then it must be getting closer and closer to that point. To see if you agree with this statement or not. And feel free to pause the video until you've come up with your own answer. So the correct answer is that this is not a true statement. So the correct answer is B, it's false. What's an example of this? Suppose an object is moving to the right with a velocity of 5 meters per second, plus 5 meters per second. It's along the positive x-axis. And let's say that its acceleration is minus 3 meters per second square, right? So what does that mean? We know from the previous example that that would mean that the object is slowing down as it moves to the right. So what is the direction of the acceleration? The acceleration clearly is to the left, right? And so the acceleration is pointed to the left, but the velocity is to the right. The object is moving to the right. So it's not true that if an object is accelerating towards a point, it's moving towards that point. That's not true. In this case, you can see that the object is moving away from that point, even though its acceleration is pointed towards that point. Okay, so an important thing to remember is that the direction of motion of an object, I mean, this is completely obvious, and it's so obvious that it doesn't even make sense to say it because it's like a definition. But still, I find that a lot of students get confused by this. So I'm stating it. The direction of motion of an object is really the direction of its velocity, not its acceleration, right? Okay, so an object does not necessarily have to move in the direction of its acceleration. All right, now coming back to this slide for a moment, you know that if the object's velocity and acceleration point in the same direction, the object will be speeding up. And if its velocity and acceleration point in opposite directions, the object will be slowing down. Now think about when you toss a ball straight up, right? When you toss a ball straight up, what does it do? What does the ball do as it's rising up? Does it speed up or slow down? Obviously, the answer is it keeps slowing down, slowing down, slowing down until it gets to the highest point, and then it starts speeding up as it comes down. So, what can you tell me about the direction of the acceleration of the object as it is on its way up? The answer is the acceleration must be pointed downwards because the velocity of the object is pointed upwards. So, when you toss a ball, the velocity, when you toss a ball, and the ball is rising, its velocity is pointed upwards, so that means its acceleration has to be pointed downwards, right? And that causes the ball to slow down until it gets to the top. And then when it's on its way down, the velocity is pointed downwards, and we know that it keeps speeding up as it's falling. So what do you think is the direction of the acceleration? Again, the acceleration would be pointed downwards because we know that when the velocity and the acceleration point in the same direction, an object speeds up, and that's what happens for a ball that's falling, an object that's falling. So you know that when an object is thrown up, we say that this is free fall. When an object is moving under the influence of gravity, the acceleration always points in the downward direction. Okay. All right, so that would also be an example of a situation where the acceleration of an object, like the ball thrown example that we just discussed, the acceleration of an object points downwards, but if the ball is on its way up, then the ball is moving away from the point towards which the acceleration is directed. So just another example that if an object is accelerating towards a point, it does not necessarily mean that it's moving towards that point. Okay. All right. Um, Here is a summary of all the kinematic variables that we discussed in this chapter. Position in one dimension is just I hat times x. In three dimensions, it's I hat x plus j hat y plus k hat z. The displacement is just the change in the position. So it's I hat delta x. The average velocity is the change in the displacement. So it's the displacement divided by delta t. The instantaneous velocity is the same thing, but with the delta t tending to 0. So it's just I hat times dx dt. Yeah, so this is what we just discussed. Limit delta x over delta t is dx dt. So that's we talked about how that comes about. And then average acceleration is very similar. It's the rate of change of the velocity. So it's I hat delta v divided by delta t. And the instantaneous acceleration is just the same thing, delta v over delta t in the limit delta t tends to 0. So you get the instantaneous acceleration. So the most important takeaway from here, I mean, just to put it even more succinctly, is velocity is equal to dx dt and acceleration is equal to dv dt. All right. So we are now going to talk about some examples of applying these. So this is a good example that's worked out in your textbook. So I'm not going to discuss this. I'd highly recommend trying it on your own. And if you can't, then you can look at it worked out in the textbook. Let's do a standard run-of-the-mill example. So you're given an acceleration, which is a function of time. A is equal to minus 60. And you are given the velocity of the particle and the position of the particle at some initial time t equals 0. So from there you have to find the particle's velocity as a function of time and the particle's position as a function of time. So let's give this problem a try. So you're told that a as a function of time, the acceleration of a particle is minus 60. And you're also told that at t equals 0, the position of the particle is 3 and the velocity of the particle is also 3. So this is 3 meters, this is 3 meters per second. All right. Okay, so let's see how we would find out the velocity as a function of time. So we know that the acceleration is, so we're going to use, essentially all that we're going to do is we're going to use these definitions, that velocity is equal to dx dt and acceleration is equal to dv dt. That's all that we're going to do. So we know that dv dt is the acceleration. So dv dt is minus 6t. So that means we can find the velocity by just taking an antiderivative of the acceleration, or the integral of the acceleration. So uh, velocity would be integral of minus 6t dt plus a constant c. All right. So now you can just go ahead and do this integral. It's going to be minus 3t square because it's t squared divided by 2, and the 2 cancels out the 6, and so you're left with minus 3t square plus c. That's the velocity. And how do you find the constant c? You use the fact that at t equals 0, the velocity was 3. So that means 3 is, if you plug in t equals 0, then you just get 3 is equal to c, and you get the velocity as a function of time. That answers the first part of the question. To answer the second part of the question, you do exactly the same thing. You use the fact that velocity is dx dt. Notice that sometimes I write x explicitly as a function of times, function of time, but that gets painful. So sometimes I just write x. Even if I don't put the function of time, it's understood that it's a function of time. So dx dt is equal to minus 3t square plus 3. So that means to find x, you can just integrate this, minus 3t square plus 3 dt plus another constant of integration. So this is going to be t cubed minus t cubed plus 3t plus c. And we use the fact that at t equals 0, x was 3. So if you plug that in, you get 3 is equal to c. And so you get x as a function of t as nothing but minus t cubed plus 3t plus 3. So all that we did here was we used the acceleration and the initial data and the definitions of velocity and acceleration to find the velocity of the particle at any time t and also the position of the particle at any time t. So with these two boxed functions, we know everything about the motion of the particle. If we are interested in where the particle was at t equals 107 seconds, all we have to do is just plug in 107 and we would get the x, the location of the particle at that time. And we would plug in 107 into the velocity function and get how fast the particle is moving and in what direction at that time. Right? So we have fully specified the motion of the particle. If we want, we can also use x as a function of time and plot it and get a position time plot for our particle. So we know everything about the motion of the particle. All right. Now there is a there's a very important special case here when the acceleration is constant. That's what we're going to talk about next. So in many types of motion, the acceleration is either constant or approximately it's constant. If the acceleration is constant, then it turns out that you could just do the calculus once and for all and just derive some results, which derive some algebraic equations, which you can use whenever you have a situation where the acceleration is constant. And so you can save all the hassle of doing all this calculus that we just did, right? So that's what we're going to do next. We are going to look at a situation where an object is moving in one dimension and has a constant acceleration, a. We know its initial velocity. I mean initial meaning at time t equals 0. We know what its velocity is and we know what its position is. And then in terms of the velocity of these quantities a, v0 and x0, what we want to do is we want to find its velocity as a function of time and its position as a function of time. And then we'll do this one as well. We'll find its position as a function of velocity or velocity as a function of position. So this is going to be very, very similar to the example that we just did, but now the acceleration is going to be constant, which means that it's even easier to integrate, right? The integral part is going to be even easier. All right, so let's just go ahead and do this. So we have a particle which has a constant acceleration a, and we are told that at t equals 0, x was x0, the position of the particle was x0, the velocity of the particle was v0. Okay, now let's just do exactly what we did in the last example, and I would recommend doing this yourself and just then check on the next slide whether you get the same answers. So so I'm not doing anything new here at all. I'm doing exactly the same mathematical manipulation that we did in the last example. All right, so we know that a is constant, so let's use the definition of velocity, definition of acceleration. dv dt is equal to the acceleration. So dv dt equals constant, which means that v is equal to the integral of this constant plus a constant of integration. So if a is a constant, then integral of dt, you can pull a out of the integration. So you're left with integral of dt, and integral of dt is just t. So v is equal to at plus c. And then to figure out what the c is, we can use the fact that at t equals 0, v is equal to v0. So that means v0 is equal to c, or in other words, you get this equation v equals v initial plus at. I call this the first kinematic equation. Okay. All right, so this is our v as a function of time. It's just uh, v initial plus the acceleration times t. So this is our equation. So this is the answer to the first part. All right, now what about the answer to, what about the second part? So we can start with this equation for the velocity that we just derived, and we can use the definition of velocity, which is that dx dt is v. So that means dx dt is v0 plus at, and so we can find x by integrating this quantity on the right side. So if you integrate it, so it's integral v0 plus at dt plus some constant of integration. So if you do this integral, you get v0t plus half a t square plus some constant, and that is x as a function of time. And to evaluate the constant, you would plug in at t equals 0, x is equal to x0. If you do that, you are going to get c is equal to x0, like the constant is just equal to x0. And so you get this equation x as a function of time is simply x0 plus v0t plus half a t square. So we have successfully found x as a function of time, and this is what it is. All right. Now, these equations can be used. This is called the second kinematic. I mean, I call this the second kinematic equation. Now, these two equations are true whenever the acceleration is constant. So if you know that you have a situation where the acceleration is constant, then you can just save all this calculus manipulation and jump straight to these equations, right? And so you have the advantage that you can just deal with algebraic equations rather than have to do calculus if the acceleration is constant, right? Okay, now in some problems it's more convenient to get rid of it's convenient to get rid of the time variable and express v and x directly in terms of each other, right? So let's just quickly do that. I mean, that's a little bit of algebra, but there is nothing conceptually, there is nothing difficult about that at all. Suppose I wanted to get an equation connecting x and v, right? So no t. I don't want t in this equation. So how can I do that? I could take the first kinematic equation and isolate t from there. So from the first kinematic equation, you see that t is equal to v minus v0 divided by a. And then I can just plug that into the second kinematic equation, and I would have an equation in which the t's are all gone and all I have are v's and x's, right? If you do that, it's a couple of lines of algebra, but if you do that, the equation that you're going to get is v square, v final squared equals v initial square plus 2a x minus x initial. And that is called, by me, the third kinematic equation. I keep saying by me because that is what I remember my high school teacher calling these. I haven't seen them called as such in any textbook, so it's just my habit to call these as the first, second, and third kinematic equations. Okay, so these are the kinematic equations, and they are valid. And please keep this in mind. These equations are valid only when the acceleration is constant. Only when acceleration is constant. They are not valid if the acceleration is varying. So for example, the problem that we did just before this, where the acceleration was minus 60, the kinematic equations have zero relevance in that situation or any situation where the acceleration is variable. You can only use the kinematic equations if you know that the acceleration is constant. So that's a very common mistake which I find students making. They would just apply the kinematic equations wherever they see the word velocity and acceleration, but keep in mind that they only apply when the acceleration is constant. All right, so I'm going to end the video over here.